Welcome back. We were discussing heat exchangers, and particularly we were trying to do some sort of analysis. I have told that we will not derive any formula, but we will just give you the formula. So, that will be some sort of a recapitulation, and while I will provide you with the formula for heat exchanger analysis, we will also do some sort of, we give also some sort of explanation to it. So, we have done the first method, which is very basic, that is for that is LMTD method or log mean temperature difference method. The mean temperature difference for either a parallel flow heat exchanger or a counter flow heat exchanger is given by some sort of a logarithmic term. So, that is why it is called log mean temperature difference, or in abbreviation LMTD. And if we go to the slide once again, so the formula is given over here, and then once we know what is LMTD, which is the mean temperature difference for the entire heat exchanger. So, we get the Q, that is the rate of heat transfer, is equal to U m into area into delta T L m, where delta T L m is given at the top. Now, here I like to tell you one thing, the U m is the mean overall heat transfer coefficient. It is dependent on area. Sometimes we find the heat exchange area that is different, particularly for a tube. If you take a circular tube, inside the circular tube you have got one heat transfer area, and outside the circular tube you have got a different heat transfer area. So, heat transfer area is relevant when you have got convective heat transfer, which mostly we are concerned. For radiative heat transfer also it is important, but we are mostly concerned with convective heat transfer, and that area depends whether you are considering it from inside of the tube or considering it outside the tube. Now, depending on that, U m will also be different. So, U m is area dependent, and here we have got this formula Q is equal to U m into A delta T m, and delta T 1, delta T 2, everything has been given for counter flow and parallel flow. I have explained it. There could be a special case. In case of counter flow, the quantity, the heat capacity rate, if that becomes equal for both the streams, that means for the hot stream and the cold stream, then we have to take the mean temperature difference simply as delta T or delta T 1 or delta T 2. Let me explain it, or we can explain it going to some sort of a previous slide. So, let us go to this slide. So, here you see heat capacity rates are same for both the hot fluid and cold fluid. So, here the temperature difference will be delta T T H I minus T C O. Here it will be again delta T. We can call them delta T 1, delta T 2. But everywhere in the heat exchanger, the temperature difference will be delta T, and that should be the mean temperature difference. Obviously, that should be the mean temperature difference. Now, what we have done, if you see that based on these 4 temperatures, 2 temperatures at the inlet end and 2 temperatures at the outlet end, we have done the analysis. This is very important, and this is what we can do, because these 4 temperatures are measurable and known. Other temperatures are within the heat exchangers. The fluid stream temperature at other point are within the heat exchanger. A direct measurement is not possible. So, we have to have the performance of the heat exchanger based on these 4 temperatures. Okay. Now, what we get? We get a formula by which, by the same formula, we will have the rate of heat transfer for both parallel flow heat exchanger and counter flow heat exchanger. Now, the question is, there are many other different types of heat exchanger. What do we do for them? What we do is like this. The LMTD shown in the previous slide is not applicable for heat transfer analysis of cross flow and multipass flow heat exchangers. Multipass flow heat exchangers, the thing is that one can think of a multipass flow heat exchanger like this. Let us say this is a multipass flow heat exchanger. Let us say hot fluid is entering here, hot fluid is going over here, and as far as cold fluid is concerned, it is entering here, it is coming out here, and hot fluid is from here to here. So, you see, for the top branch of the cold fluid, it is a parallel flow, and for this branch of the cold fluid, it is counter flow arrangement with the hot fluid or hot stream. So, if we have this kind of a heat exchanger which is having 2 pass for the cold fluid, then this heat exchanger we can neither call it a parallel flow heat exchanger, nor we can call it as a counter flow heat exchanger. For this kind of heat exchanger, there are many examples, even much complex example. Cross flow heat exchanger is another one, where the we have not derived any formula for cross flow heat exchanger, but how to do then this analysis. But whatever may be the flow arrangement, it goes without saying that these 4 temperatures, let us say this is 1, 2, 3, 4, these 4 temperatures are very important, and based on these 4 temperatures one can determine the mean temperature for the mean temperature difference of the heat exchanger. So, one method has been suggested which is very useful method, that we will use the LMTD formula only, but we will multiply it with some sort of a factor f, and with that we will get the mean temperature difference. This f will depend of course on some parameters. One is this parameter, it is called P, and the definition of P, expression of P has been given. Heat actually transferred to the fluid, which would be transferred if same cold fluid temperature was raised to the hot fluid inlet temperature. Hence, it is temperature effectiveness of heat exchanger, this is P. And then this also is important, this is the ratio of heat capacity rate, Cc for cold fluid and Ch for hot fluids. So, Cc by Ch, that is R, ratio of m dot Cp of cold fluid to that of hot fluid, and is called heat capacity rate ratio. And then it will also depend not only on these physical parameters, it will also depend on the flow arrangement. So, generally what we get, we can express by Q the heat transfer by this expression, where U is the overall heat transfer coefficient, A is the area, F is the correction factor. This is what we have introduced now, which will be a function of P and R, and of course, the flow arrangement, and then delta T Lm counter flow. For counter flow heat exchanger, whatever delta T Lm we will get, whatever LMTD we will get, considering counter flow arrangement. Then F I have told that it depends, F is a number, and it is of course like this. In counter flow arrangement we get maximum amount of heat transfer, that is most conducive for maximum heat exchange between two streams. So, the F value will be equal to 1 if we consider counter flow heat exchanger. Now, if it is not counter flow heat exchanger, then obviously the value will be less than 1. So, we will have this kind of curves. It has been already calculated and made available for our ease of calculation, ease of estimation. So, here you see this is your F and this is a function of P, and where R is taken as parameter. So, different curves are for different values of R, and then I have told that it depends on the flow arrangement. So, this is for a particular type of heat exchanger where there are two passes like this. This is for another heat exchanger where there are 4 passes like this. So, for each and every heat exchanger arrangement, we have got curves like this. So, basically we have to pick up the curve for a specific fluid flow arrangement. Then we have to know the value of P and R, and from this particular curve which we have selected already for the heat exchanger, we have to get the value of F. Then we can use the formula which we have already mentioned, and we can get what is the rate of heat transfer. So, you see this is what I was telling, F is a function of P, R and flow arrangement. That is what we can see from this particular slide also. So, this is one way of determining the heat transfer rate. This is a very direct way. If the 4 temperatures are given, temperatures at of the 2 streams at both the inlet and exit. So, then from there we can determine what is our rate of heat transfer. So, this is one typical kind of analysis, this this kind of formula which is FLMTD formula that can be used. So, let us try to understand what kind of, suppose we know the 4 temperatures. At the beginning we try to design some sort of heat exchanger. We know Q, that is the rate of heat transfer which we have to go for, and the 4 temperatures which we like to have. So, these 2 things are fixed, and then we have the flow arrangement, that means whether what kind of tube diameter etc., whether it is counter flow or parallel flow. So, those kind of arrangement and tube diameter, that means geometry etc., are the type of geometry that is known. So, you know Q, you know delta T Lm, then overall heat transfer coefficient, that also is known because the tube diameter you have selected, and from there you know what is the heat transfer coefficient. So, basically one can calculate A. Once you calculate A, then probably either the number of tubes or the tube length you can calculate. So, this is a method which is very suitable for design, for new design. Of course, the way I have told, it is not as simple as that. because U and A, they could be interrelated. Even delta T and Q, we cannot separate them out the way I have told that separately I know Q and delta T. So, there could be some sort of iterative procedure needed, but for design if the 4 temperatures are known, then this FLMTD method is a very good method. Unfortunately, in many of the cases these 4 temperatures are not known. We know let us say only 2 inlet temperatures and we know some other quantity. So, then the FLMTD method becomes a very roundabout method, a tedious method, not impossible to apply for those kind of analysis or problem, but it becomes little bit time consuming, tedious, more number of iterations are to be needed. So, there should be some other method where the life is little bit simple. So, that method is known as effectiveness NTU method, and we are going to have a very brief overview of effectiveness NTU method. Applicable when the inlet and outlet temperature of the fluid streams are not known. 4 temperatures are not known. Method is based on the fact inlet or exit temperature difference are function of these 2 things. That means, one is U A by C C, or it could be C mean, and another is heat capacity rate ratio. Now, in dimensionless form we introduce one term called C star, what is it is known as capacity rate ratio or heat capacity rate ratio. This is C mean by C max, where C mean and C max are the smaller and larger of the 2 magnitudes of C H and C C respectively, and C C star will be less than equal to 1. So, this is one important parameter for our analysis. The exchanger heat the exchanger heat transfer effectiveness or this effectiveness epsilon, it is the ratio of actual heat transfer rate in the heat exchanger to the thermodynamically limited maximum possible rate of heat transfer. So, what is that? Q dot actual heat transfer rate can be obtained like this. Q dot is equal to MCP H, that means MCP of the hot fluid side multiplied by the temperature change in the hot stream, or it is the m dot Cp of the cold fluid side multiplied by the temperature change of the cold stream. If Ch is greater than Cc, then we will get this relationship, otherwise we will get this relationship. The maximum heat transfer possible, let us see how we can get this. The fluid that might undergo maximum temperature difference is the fluid with minimum heat capacity rate, C mean. Therefore, the maximum possible heat transfer is expressed as Q max is equal to m dot Cp C, that is Thi minus Tci if Cc is less than Ch, or Q max is equal to m dot Cp H multiplied by Thi minus Tci. So, this will be the maximum amount of heat transfer. So, effectiveness we can define like this, depending on our whether we like to use Ch or Cc, the effectiveness can be used like this. So, you see this is the maximum temperature difference possible without violating thermodynamics or without violating second law. So, this is the definition of effectiveness. The above equation is valid for all heat exchanger flow arrangement. The value of epsilon ranges between 0 and 1. If the effectiveness is known, equation provides the expression for determination of Q. So, suppose I know the effectiveness of the heat exchanger, then Q can be determined simply by m dot Cp multiplied by Thi minus Tci. Generally, inlet temperatures are known. So, you see the advantage of using this method. Generally, inlet temperatures are known, or even as the basis of the design, the inlet temperatures are known. So, if I know the inlet temperatures, and then if I have already decided what could be the effectiveness of the heat exchanger I am going to design. So, my effectiveness that is also known, then I will get the Q value, or vice versa. Suppose the inlet temperatures are known and I know that how much heat I have to extract or I have to supply, then using this particular formula I can know the effectiveness of my heat exchanger. Now, we come to the next parameter. Next parameter is NTU. The full form of NTU is the number of transfer unit. It gives some idea regarding the size of the heat exchanger. So, NTU is defined as AU divided by C mean, where A is the area, U is the overall heat transfer coefficient, and C mean is the minimum of either of CH and CC. So, once we have got NTU, as I have told that it is indicative of the size of the heat exchanger, it is also indicative of the residence time of the fluid in the heat exchanger. So, basically it gives idea regarding the heat transfer, whether the rate of heat transfer will be very large or very small, something like that. So, relative it is a relative kind of a thing. For same kind of heat exchanger, if we have two values of NTU, the higher value of NTU gives that the size of the heat exchanger is more, or inside the fluid stays for a longer time, like this. And then what is important, the effectiveness and NTU, they are uniquely related. For counter flow, the following expression is obtained. This is between effectiveness and NTU. Okay. And it will be the same if Cc is less than Ch, the result will be the same. In case of parallel flow, a similar analysis can be applied to obtain the following expression. This expression we will get for parallel flow. So, you see these expressions are little bit complex, but there is a unique relationship between NTU and effectiveness. If we know one, we can determine the other one. In many of the cases, what we have got curves for effectiveness or NTU. There are results which are expressed graphically in the form of curves. So, then it becomes easier. Of course, nowadays with the help of digital computing, calculation of this kind of relationships or tackling this kind of relationship is child's play. So, it is not at all difficult. But you see, I have given, just like before, I have given the relationship for parallel flow and counter flow. There could be other kind of flow arrangement. There could be other kind of flow arrangement, and for them what are we going to do? Let us discuss some sort of special cases. One special case is that the heat capacity rate are equal for both the fluids. Then C mean by C max is equal to 1, and effectiveness is given by NTU divided by NTU plus 1 for counter flow, and effectiveness is this value for parallel flow. C mean by C max is equal to 0. This is another special case where we will have one of the fluid stream is changing its phase. If some fluid stream changes its phase, then the temperature difference between the inlet and outlet is equal to 0. Then for finite heat transfer, the C value has to be very large. This if there is some finite amount of heat transfer between the inlet point to the outlet point, and from there we get that C mean by C max is equal to 0 as in case of boiler and condenser. So, we will have this kind of, the equation becomes epsilon is equal to 1 minus exponential of minus NTU. In general, epsilon is a function of NTU, C star and flow arrangement. Again, just for as we have got for F different kind of curve. So, for this kind of relationship also we can have different type of curves. The two cases which we have shown for LMTD method, the same two cases here it is shown. So, this is the flow arrangement. For a particular flow arrangement we will get a typical curve. So, this is C mean by C max, and this side we will have NTU, and as a function of NTU we will have the effectiveness of the heat exchanger. So, effectiveness of the heat exchanger, that is a function of NTU, that is dependent on the flow arrangement and also dependent on the C star value, that is C minimum by C maximum. This is for another case. So, there are host of curves like this. So, using these curves we can employ the effectiveness NTU method and we can do calculation. Now, depending on type of problem, we have to adopt either the FLMTD method or the effectiveness NTU method. In many cases, the iterations required for FLMTD method can be avoided by taking effectiveness NTU method. We will pick up certain examples to clarify these points, and then we will see how the heat exchangers are very relevant for waste heat recovery. Thank you.